Today we will be solving this problem called projects. So we will be given n projects. Each project has a starting and ending day and some amount of money that we would get as a reward. And we can only attend one project during each day. And our goal is to maximize the amount of money we can earn. In this example, we are given 4 projects, and the optimum answer is to choose the first and last project for a total score of 7. Notice here that we cannot choose project 2 and 3 because this project ends in day 6 and this one starts in day 6. So during day 6 we cannot attend 2 projects. So let's head to the drawing board to see how we can solve this problem. To get a better understanding of this problem, let's consider this example. So say we have 8 projects. I went ahead and gave a label to each one of them from A to H, and I plotted them here. So just to make sure we are on the same page, I would say that the combination A, C, H is a valid combination because the project A goes from day 1 to 4, project C goes from day 5 to 7, and project H goes from day 8 to 10. So this would give us a total score of 55. So our goal is to maximize this value. So the first thing that comes to mind here is to generate all possible combinations and see if we can learn something from that. And just as a remark before proceeding, the order in which we will process this project is very important. For example, if we process project C before project E, we would not be able to generate the combination EC, because in this case we will only check if project E can come after project C. So in general, we are interested in what it means for project Y to come after project X. So right off the bat, this means that Y.start should be strictly greater than X.end. This implies that Y.end is also strictly greater than X.end because each project's end date is larger than or equal to its starting date. So let's go ahead and reorder this list based on the ending date. So this is the order in which we will process the project. We will start with project E. This is just the beginning, so the only possibility is to take project E by itself for a score of 10. Next, we will process project A. We cannot combine it with project E, so all we get is project A by itself with a score of 20. Next is project D. We cannot combine it with project E because they both overlap on day 2. So all we can do is add project D with 25. Next is project B. This is the first combination that we can generate. So we have B by itself with a score of 30 and B, or rather E along with B for a score of 40. Next is C. We can actually combine it with both A and E. So we get C by itself for a score of 15, A with C for a score of 35, and E with C for a score of 25. Next, we will move on to F. So we can have F by itself for a score of 35, or we can combine it with E for a score of 45. Moving on to G. G can be combined with D, A, and E. So we get G by itself with 40, AG with 60, DG with 65, and EG with 50. And if you've been paying attention so far, you can notice that for any project, for example for project G here, we were able to combine it with a prefix of the list we've generated so far. So for example, here we've been able to combine it with this prefix. And we stopped at B because we couldn't combine B and G since they overlap at 6. So let's continue with H. We can have H by itself for a score of 20, or we can combine it with E, and this will give us a score of 30. We can combine it with A for a score of 40. We can combine it with D as well for a score of 45. We can also combine it with B for a score of 50. We can also combine it with any combination that ended at B. So we would get E, B, H for a score of 60. And we can also combine it with any combination that ended at C. So we would get CH, ACH, and ECH with scores 35, 55, and 45. And here too you can notice that all valid combinations with H form a prefix of the list we've generated so far. So the optimal answer in this case is this combination DG with a score of 65. But this process is very slow. In fact, it is worse than quadratic because each project we process not only has to be combined with all previous projects, but it also generates new combinations. And the fact that it generates new combinations is our first point of attack. I want you to focus on this part here. So basically, these are all the possible combinations that end at C. And these are all the possible combinations that end at H and have the previous project as C. So basically we see that there is some redundancy here. The fact that we process all the possible combinations that end in C is a bit superfluous because we are only interested in the maximum value here. So we do not care at all about what came before C. So the only thing that we need to check to see if we can combine H with these projects is their endpoint. So anything that comes before the endpoint is irrelevant. And this means that we can group these three combinations into a single one where we only care about the last project and the maximum value we can achieve here. So the maximum value we can achieve here is 35. We can do the same thing for B here, and we will be only left with one project with maximum value 40. The same for F here, so we will get F with maximum value 45, and for G, we will get G with maximum value 65. And finally for H, we will get H with maximum value 60. Here for G, it is more interesting. We said that we could combine G with this whole prefix, and the maximum value here is 25. That's why the value for G was 65, 40 plus 25. For H, we said that we could combine it with this whole interval, and the maximum value over this interval is 40. That's why we got 60, 20 plus 40. So what you can notice here is that these values are not strictly increasing. So here we got 40 and it went down to 35. Same thing here, we got 65 and it went down to 60. So basically what we need to do to solve this problem, or rather the dynamic programming formula is the following. So let dp of I, where I is a project and it goes from 1 to n. So this value dp represents the maximum value we can achieve over all combinations that end in I. So this will be equal to the value of I plus the maximum over dp of j, where j ranges over all the projects pj, where pj.end is strictly less than pi.start. And the final answer in this case will be just the maximum of dpi over all i's. But the implementation of this method will be tedious. First of all, these values range between 1 and 10 to the 9, so we cannot just store them. We need to perform coordinate compression first to bring these values to a range less than 2 times 10 to the 5th. So in order to avoid all that headache, we can take advantage of a data structure such as a set that stores finishing times and the maximum value that we can achieve up to that finishing time. So let's rework this example using the set to see what that would look like. So our set will contain the finishing time and the maximum value we can achieve up to that finishing time. So at the beginning, we will only have the pair 0, 0. So we are practically done. We finished at time 0 and the score we've achieved so far is just 0. So we will process projects again in the same order. So for project E, the only pair that we can combine it with is this pair 0, 0. So we get a finishing time of 2 with a max score of 10. So let's move on to project A. Basically, project A starts at time 1, and these are the finishing times I have so far. So I can use something like a lower bound to find the project that starts right before this time. In this case, it is just 0, 0, so I will get a finishing time of 4 with a score of 20. Next, for D, it will be the same thing. The only finishing time I can match is this one, so I will get a finishing time of 5 with a score of 25. Now I'll move on to B and it will start to get interesting. So what is the lower bound of 3 in this case? It is 2. So the max I can achieve is 30 plus 10, which is 40 with a finishing time of 6. And that's indeed what I get here. Next, I will move on to C. So I need to find the finishing time strictly less than 5, and in this case it is 4 with a score of 20. And technically, to do this, I can just lower bound 5 with -1, for example, and move the iterator one step back. So this will give me a finishing time with 7 and a score of 35 to match what we get here. But this is not actually what we need for our implementation. So if we keep things like this, a project with a starting time with 8 will just lower bound this value here and it will get a match with this 7 for a maximum score of 35, whereas we could have achieved a maximum score of 40 if we picked 6. So basically we need to maintain this in a sorted manner. And to do that, it's pretty simple. We can just keep track of the maximum so far, and for each value, we should just max it with that. So this should be 40 instead. And this makes sense if we are able to match in combination with a finishing time of 7, we can also match one with a finishing time of 6. So the process I have been doing should be updated in such a way that we max this value with the max so far each time. So now we can move on to project F. The lower bound of 4 in this case is 2, so I'll get a finishing time of 9 with a max of 45. Next is G. The lower bound of 6 in this case will be 5 with a max score of 25. So I get a finishing time of 10 with a max score of 65. And finally for H, the lower bound of 8 would be 7 here. And C here, if we had 35 here, we would have missed the max score of 60 that we can achieve here. So we need to make sure to always max this value with what we've got so far. So for H, we'll get a finishing time of 10 and a max score of 60. And again, we need to max this 60 with this 65, so this will be 65. And the final answer will be just 65. So to sum up, the first thing we will need to do after processing the input is to sort the array by finishing time, then using a set of finishing times and max values. This should be of type long because it can reach values up to 10 to the 14. So with this set, we will process the projects in the order we mentioned, and each time, for each starting time, we need to find the element in the set with a finishing time strictly less than the starting time we have here, and we need to maximize that. So basically we need to process n projects, and for each project we need to perform 2 operations with the set. Each costs us log n, so the total complexity would be n log n. So this is pretty much it. Let's move on to the code. So this is our program. I started by making some defines for long and for new line. Next, I will define a structure so that my code remains organized. I will represent the project with a structure that has the following elements. So it has 3 variables, a start, an end, and the value. And I also went ahead and implemented the operator less than, so that I can sort a vector of projects right away. And the operator here is, as we said, we're gonna sort the projects by ascending order with respect to their finishing time. For my main project, I start by reading the number of projects. Then I declare a vector with my struct of size n. Then for each element, I read its starting, ending, and value. Then I just go ahead and sort the project. Next, I define the set that we mentioned. Make sure to have long here since the max value can be quite large. Next, I insert the first element as we did here. So we said we're gonna insert 0, 0. Next, I initialize my answer with 0. This is the same answer I will keep maxing after each project process. So I will loop through the project from 0 to n, and for each project I need to find the finishing time that came just before it. So to do that, I use the lower bound method that comes with sets, and I give it the starting time of the project, and for the second value I give it a -1. So doing this, I make sure that I will recover the finishing time that has either the exact starting time and the minimum value, or a starting time greater than my actual starting time. But what is more important is that by moving the iterator one step back, I will get what I desire, which is precisely the finishing time, the largest finishing time that is valid. So my answer here will be just the maximum of what it has been so far, along with the value I get from project I, plus the second value in my iterator here, which represents the maximum value I get for that particular finishing time. Next, I will answer this new finishing time with the maximum answer so far. And finally, I just output the answer. So let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.